Good morning. Once again, this is Professor Grenfell with my ongoing lecture series for Math 12 Statistics at Riverside City College. And today we're going to just quickly delve into Chapter 4 on probability. And we're not going to spend way too much time on this. In fact, we're only going to go over the first section of this chapter to just give us the basic concepts of probability. So let's go over the preliminary definition. Okay, so first, a probability experiment is a chance process that leads to well-defined results. These are called outcomes. So what do we mean by an outcome? Well, that is the result of a probability experiment. Probability experiment there. Abbreviate them nicely. So to just give you a few possible, hypothetical examples of probability experiments, and not necessarily all of the potential outcomes, but just to kind of give us some examples to think about. As an example, we could say we'll flip a coin. That would be the probability experiment. Why? Well, it's a chance process. We don't know what side of the coin is going to land on. There's two well-defined results. It could either land heads up or tails side up. Notice here we're excluding the possibility of the coin landing on its edge. All right. So sometimes there are instances where we have to kind of restrict our purposes to only deal with outcomes that are going to be, in the realm of possibilities. You could say, well, pick a card, right? If the cards are all shuffled up and I draw one at random, then that is a chance process. And the particular card that I grab is going to be that outcome, right? So there's one well-defined outcome for that. You could say, here, I'll just add in another. You could say, I'm going to drive my car to the store. What could happen? I could get in an accident, or I could not get in an accident. We could say those are the two outcomes that I'm looking at, and there's some small chance of us getting in an accident. That's why they call them accidents. Right? So those are just a few examples of probability experiments and their corresponding set of outcomes. So the next vocab concept is sample space. That is the set of all possible outcomes for one specific probability experiment. Okay, and so here we can see some more examples of probability experiments and then the outcomes of that experiment for one particular trial. Okay. And the set of all outcomes is what we call the sample space. So in this first experiment, you toss one coin. The sample space is, well, there's two outcomes. We could land heads or tails. And so there is the complete set of all outcomes. We roll a die, okay? Here, we're going to probably assume that a die is just a standard cube. We're not dealing with weird alternative faced dies. So if we roll a die, then it could land with 1 dot, 2 dots, 3 dots, 4 dots, 5 dots, or 6 dots, or numerals, or whatever. So there's our sample space. We answer a true-false question. Okay, the sample space would be true-false. Toss two coins, right? Then we have to keep track of both coins, right? So we could have both heads, both tails, the first one heads and the second one tails, or the first one tails and the second one heads, right? So there we kind of have to keep track of what each individual coin is doing at the same time. So we could say our experiment was we drove in our car and the sample space would be, let's see, we had an accident, we didn't have an accident. Those would be the two outcomes. All right, in this first example, example 4-1, it says says to find the sample space for rolling 2 dice. So I'm going to kind of organize my thoughts like this. Let's say here we have the information for what die number 1. So dice is plural, die is the singular. Okay, and then up here on the top we can say what die number 2 is doing. Okay, so picture these. You're rolling them one at a time, or you color one of them green, the other one red, so that you can kind of keep them distinguished. But we do need to pay attention to what each one individually is doing. So on die number 1, we could roll a 1, 2, 3, 4, 5, or 6. Okay. For die number 2, we could roll a 1, 2, 3, 4, 5, or a 6. All right. So most of the time, it doesn't matter what each individual die does, because a lot of the times we're interested in taking the sum of them. But here, when we're considering the whole complete sample space for just rolling the dice themselves, right, then we will have essentially 2 pieces of information to look at for each of these outcomes: what die number 1 says and what die number 2 says. So here, die number 1 says 1, die number 2 says 2. So that is a different outcome than rolling a 2 on the first die and a 1 on the second die. So notice this and this would give us the same sum, right? But essentially there's 2 different ways to roll a 3 when you're rolling 2 dice. So here we can go ahead and list all of them out. All right. Okay, so there, I filled it all in. Well, sorry, I have not filled it in. I have said, here, you kind of get the idea. You fill the rest of it in. So I'll allow you to do that. So oftentimes, we're not quite so interested in the sample space itself, like what the individual outcomes themselves are. Most of the time, we are concerned with the size of the sample space, right? So in other words, how many different outcomes are there? And so in this case, the size of the sample space is 36. And the majority of Chapter 4 that we are not going to be covering goes into various different techniques that are to varying degrees of complexity on essentially how to kind of combine and count various different things and see how that affects the probability. For our purposes, we don't really need to get into all of that. So as long as we can count up the total number that are in the sample space and the total number that are in our particular event that we're looking for, we don't really need to do much else. So let's take another look, another example of finding the sample space. In the next example, we're going to be looking at the probability experiment of selecting at random 1 card out of an ordinary poker deck playing cards. So what is the sample space itself, right? We know pretty quickly that there are 52 different outcomes. So in other words, the sample space has 52 different possibilities, or 52 different outcomes, results, and the sample space itself is just a listing of all of those results. So here we can, put a little symbol for the specific card itself for each one of these, from the Ace of Hearts all the way up to the King of, oh my gosh, I can't draw these, the King of Clubs, and listing out all 52 of these in between. So that one, I'm going to refer you to their illustration of it, where they have listed out every single one, every single different playing card in the whole deck. That is our sample space. Those are the set of all potential different outcomes. We'll have 52 cards that we can draw from. Next, let's find the sample space for the gender of the children if a family has 3 children. And we'll denote B for boy and G for girl. So I've got this written as gender of children. Here the family's going to have 3 children. We're using B for boy and G for girl. And so here, one way to do this is to just go through systematically and enumerate, that is, list out all of the different possibilities for this family and their 3 children. So we could say the first child is a boy, the second child is a boy, and the third child is a boy. That would be one way to do it. We could have 2 boys and then 1 girl. We could have a boy, a girl, and then another boy. We could say a boy, and then a girl, and then a girl. And similarly, we could say here, a girl, followed by a boy, followed by a boy, girl, boy, girl, 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 boy, and then finally all 3 children are girls. All right, so is this really necessary? Well, let's see. Yeah, this is different. This is a different family that has 2 elder siblings, both boys, and the youngest is a girl, versus here, this one, for instance, the oldest child is a boy, the middle child is a girl, and the youngest child is a boy. They both have 2 boys, 2 boy children, but that would be a different outcome when we're talking about the gender of all 3 children. The order, youngest, middle, oldest, that makes a difference. That matters. Now, one way of systematically going through and finding all of the possible outcomes, the whole entire sample space, is to form what we call a tree diagram. So this consists of a starting point, and we have line segments emanating out of this point, okay? And these indicate the different outcomes of one trial of this experiment. So for the first child, they could have a boy or a girl. Then based on each one of these, the second child, they could still have a boy or a girl, right? And then one more child into the mix, the third, they could have a boy or a girl, right? And now we have to fill in the branches for the rest of these outcomes as well. So in the instance where they had the first child being a boy and the second child was a girl, then for the third child, they do have still 2 different options. They could be a boy or a girl. And then the same thing here. If they had a girl first, they could still have a boy second or a girl second. And then, let's see, I've kind of run out of space here. A boy or a girl. And then last, boy or girl. So notice here there are 8 final outcomes. And these give us a systematic sort of way of finding and listing all of the items in the sample space. So just to kind of illustrate this, along this first path, we have a boy, and then another boy, and then a boy. So that would be the outcome B, B, B that we had up in this one here. Okay. Or, another potential is we could say, we had a girl first and then a boy and then a girl, and that would be this outcome: girl, boy, girl. That was here, girl, boy, girl. Okay, next, more terminology. An event is a set of outcomes for a particular probability experiment. Okay, it's important to notice here that the event is not the set of all possible outcomes of a probability experiment. It is, most of the time, a proper subset of the whole sample space. So the whole sample space is the set of all possible outcomes, and an event is just some partial list, some subset of that. So for example, you could say the whole sample space is every possibility for weather: sunny, partly cloudy, rainy, snowy, etc., and so on and so forth. And an event might be, well, let's see, precipitation. So you might say it'll rain or it'll snow, and that would be the event that we're looking for. So it's just an example. So here I've written weather, all possible weather conditions. That's our sample space, and then the particular event is the conditions being rainy. So that's our example. So based on this, how do we compute probability? Well, according to classical probability, here, if two events are equally likely, then they have to have the same probability of occurring, and vice versa. Two events that have the same probability of occurring are said to be equally likely. And in order to calculate probability, under this assumption, the way that we define probability is as the number of outcomes for our event, which we'll call E, divided by the total number of outcomes in the sample space. So we refer to that as S. So here, not in words, we have the formula P of E. The probability of this event is the number of outcomes in E divided by the number of outcomes in the sample space. All right, in this first example, the experiment is drawing one card randomly out of a deck of ordinary playing cards, and the event that we're trying to find the probability of, it says find the probability of getting a black 6 when one card is randomly selected. So our probability will calculate as follows. Of course, it's the number of outcomes that will satisfy that event divided by the total number of outcomes in our sample space. And here we're going to substitute in 2 because there are 2 black 6s in the deck. There's the 6 of spades and the 6 of clubs. And then we're dividing that by 52. So like I had mentioned, it's not really crucial that we draw a picture of every single playing card in the deck. It's more important that we know how many are in there that will satisfy our particular event. That is pretty, we need to make sure that we carefully count and keep track of each outcome that will satisfy that particular event. But then when it comes to the whole sample space itself, we normally just need to know the number. So this will reduce down to 1 over 26, or equivalently with the calculator, it's approximately 0.038. So that would be equivalent to 3.8%. And this is one of the 3 different ways that we can, this is all 3 different ways that we can express a probability. We can express it either as a proper fraction, decimal value that's between 0 and 1 inclusive, or a percentage that is between 0 and 100%. Okay, just quickly, example 4-6, the gender of children. It says if a family has 3 children, find the probability that exactly 2 of the 3 children are boys. Okay, so there is the event. There are 3 different outcomes that will produce the event that this family has a family of exactly 2 boys and 1 girl. So we could have the 2 boys born first and then the girl last. We could have a boy and then a girl and then another boy. That would be 2 boys. Or the eldest child could be a girl and the younger could be both boys. So here, the probability, by definition, is the number of outcomes in the event divided by the total number of outcomes in our sample space. Notice I didn't go back and re-enumerate the sample space. I just remembered that there were 8 outcomes. So there it is, 3/8 as a proper fraction, 0.375 as a decimal, or 37.5%. And whenever we round it, we'll round to the nearest 1/10 of a percent. In this next example, the experiment in each one of these instances is drawing one single card from an ordinary deck of playing cards. The first event is drawing a heart. The card we draw is a heart. Well, there are 13 hearts in the deck, and when we enumerated this whole sample space before, the number in the sample space was 52 because there's 52 different cards in the deck. Okay. So each one of these, the denominator is going to be 52, and essentially we're going to be counting up the total number of cards that satisfies whatever the condition in the event is. So in this case, 13/52 reduces down to 1/4, so we could leave it as that, or you could say it's the decimal, 0.25, or you could say it's exactly 25%. All 3 ways of saying it are all equivalent in terms of probability. A black card, right? Well, there's 26 of the cards out of 52, so that would be 1/2, or 0.5, or 50%. Equivalent, all of them. All right, the 8 of diamonds. There's only 1 of those in the deck. And so here, our fraction would just be 1/52. And just finishing that off with a calculator, that gives us 0.019, or 1.9%. The probability of drawing a queen. There are 4 queens in the deck, 52 cards in the deck. So we have a 1 out of 13. And that is equal to 0.077. We'll round it off there, or 7.7%. Now last, the probability of drawing a face card. A face card is a jack, or a queen, or a king, any one that has a picture of a person on it. Face card. There are 12 total of those. Or if we reduce this fraction down, that becomes 3 out of 13. That's another way to think of it. Within each suit, there's 13 cards, and 3 out of the 13 are face cards. That is equivalent to 0.231, or 23.1%.